When thousands of pounds of pressure bear down on a steel support, knowing precisely how it will bend is the difference between structural integrity and failure. This isolates the basic analytical unit, a two-dimensional beam element defined by end nodes, vertical point loads P, and concentrated moments M. Adding the continuous lateral force F of x across the length, we solve for two nodal variables, vertical displacement V and rotation angle V'. Capturing these discrete nodal variables mathematically is what allows us to define the continuous lateral deflection function, which predicts exactly where the entire beam will be under load. Deriving that continuous function directly through differential equations is difficult. Hamilton's principle offers a powerful energy-based alternative to bypass that complexity. Here is the central governing equation. It states that equilibrium occurs exactly when the variation of internal strain energy, delta U, minus the variation of external work, delta W, equals 0. Physically, this means the system finds its resting state when the kinetic and potential energy introduced by outside forces perfectly balances the elastic energy absorbed by the material itself. But we cannot simply plug raw force vectors into this equation. We must explicitly define both the external work and the internal energy as distinct mathematical expressions first. The first step of our derivation is constructing the mathematical expression for the total external work. This requires accounting for the three specific load types currently acting on our element: the point loads, the concentrated moments, and the distributed loads. Translating these physical forces into strict energy definitions is mandatory before we can generate any stiffness matrix for the element. This diagram shows work by point loads, P1V1 plus P2V2. For concentrated moments, it's M1 theta 1 and M2 theta 2. Lastly, distributed load work requires integrating the load function multiplied by deflection across the beam's length. To unify these three distinct expressions, we apply the small angle approximation. In solid mechanics, structural deflections are typically minute. At microscopic scales, the node's actual rotation angle perfectly equals the geometric slope of the deflection curve. Because of this equivalence, we replace the theta variables in our equation with the spatial derivative V'. By adding the modified point loads, the applied node moments, and the distributed expressions together, we get the complete equation for total external work, standardized entirely in terms of displacement and its spatial derivative. This establishes a single, unified mathematical target for the finite element formulation. With external forces defined, we evaluate the internal elastic strain energy. As this block bends, it compresses on top and stretches on the bottom. This gives us the baseline elastic strain energy equation, the volume integral of half the internal stress times internal strain. Assuming a linear elastic material, we use Hooke's law to substitute stress with the modulus of elasticity, E, times strain. This leaves an epsilon squared term. However, calculating a true three-dimensional volumetric analysis for every element in a complex structure requires massive computational overhead. To reduce this complexity, we rely on Euler-Bernoulli beam theory. The core assumption is that cross-sections of the beam perfectly flat before bending remain flat and stay perpendicular to the neutral axis after bending. This geometric constraint allows us to map a complex 3D internal strain state directly onto a simple 1D curve. Under Euler-Bernoulli constraints, internal strain is strictly proportional to vertical distance from the neutral axis and the overall curvature of the beam. Looking at this cross-section diagram, we replace the generic strain term epsilon with negative y times v double prime, the second spatial derivative of deflection. Assuming a homogeneous cross-section, the modulus E is constant. Because E and curvature don't change across the section, we pull them outside the integral. This leaves y squared integrated over area A, defined as the second moment of area, I. The resulting paired term, E times I, is the fundamental bending stiffness of the element. By extracting this bending stiffness, we have successfully collapsed a highly complex 3D material problem into a straightforward 1D line integral spanning the length of the beam. We now have complete mathematical definitions for both the total external work and the 1D internal strain energy. The next procedural step is taking the mathematical variation of the external work with respect to the virtual displacements at the nodes. Applying the same variation operator to the internal strain energy isolates the variation of the second derivative. Next, we substitute both varied expressions back into Hamilton's principle, setting their difference to 0. We have fully assembled the theoretical equation. But because it remains framed entirely in continuous calculus functions, a computer cannot natively process it using matrix algebra. To make the equation computable, we must translate the continuous deflection variable into a discrete, finite set of numbers. We bridge this gap using interpolation functions, also known as shape functions. Interpolation functions express the state of the continuous physical curve entirely in terms of the known displacement values at those discrete endnotes. We substitute these shape functions into our variational equation, replacing every continuous variable with a matrix of shape functions multiplied by nodal degrees of freedom. We then group the terms so integral operators apply strictly to the interpolation functions. Through this precise substitution, an unsolvable continuous calculus integral becomes a solvable algebraic matrix format. Executing these grouped integrals yields the precise numerical values required for the finite element model, snapping cleanly into the classic discrete structural matrix format, K times D equals F. This resulting stiffness matrix is mathematically identical to the one derived using the standard weighted residual method. If the final mathematical outcome is completely identical, why endure the complex energy-based Hamilton's principle derivation to get there? While weighted residuals are sufficient for basic static models, tracking system kinetic energy from first principles is strictly required for advanced nonlinear problems. Mastering this energy-to-matrix pipeline is a strict prerequisite for deriving mass matrices in structural dynamics and for analyzing severe beam buckling in real-world applications.